Okay, well, let me first of all introduce Sebastiano. Sebastiano Miano is a postdoc at Queen Mary University of London, working with Jenny. He got his PhD and master's from the Politecnico di Torino. And he did his PhD while visiting at EIT Digital Silicon Valley Hub in San Francisco and the University of Cambridge, where I presume met Jenny. His research interests include programmable data plane and high-speed network function virtualization with a focus on eBPF and XDP. And today he's going to be talking about domain-specific runtime optimization for software data planes. And with that, the room is yours, Sebastiano.
Thank you, Ignacio, for the introduction. So I just want to say that this talk is basically an extension of the ASPLOS talk that I presented this year. I hope I will not take like too much time for the entire talk because I extended, I have more information. Hopefully it's not too long. So first of all, let me give you a brief of context of what we really mean with software data planes. No? We know that today the data plane of software network function running on general purpose servers can be implemented in several ways. We can write our application in the kernel using kernel bypass technologies such as DPDK, NetMap, VPP, FDIO, and write applications such as OpenVSwitch, that make use of these kernel bypass technologies. But there is another possibility today that is running software data planes directly in the kernel using the extended Berkeley packet filter or eBPF that allow us to inject custom user-defined application in the kernel without having to install additional kernel modules or recompile the kernel itself. Now, if we look at the traditional approaches to compile and optimize these software data planes, what we can say is that they follow the pattern shown in this figure. We write our application using an high-level language like C for eBPF or DPDK, and this application contains the entire data plane semantic, how we parse the packet, how we read the headers, how we perform different operations on specific match action tables. Then we give our source code to a data plane compiler and optimizer that for software application is like a standard compiler like GCC LLVM that we use for generic software programs. And then this compiler will generate our network function data path binary. What is important to note here is that this binary is completely agnostic to the actual configuration, to the runtime configuration of the data plane. And this behavior is configured at runtime by reading information from specific match action tables. What I will talk let's say, in this paper, in this work, basically we are proposing a new approach to this data plane compilation. And what we want to do is to demonstrate that exploiting the network function runtime behavior, such as the content of the installed rules or the different configuration settings, together with some information coming from the type of traffic that the application is receiving, can allow us to, let's say, open up new opportunities for code specialization. In particular, I will present Morpheus, which is a system working alongside static compilers that continuously optimize the target networking code by generating every time a new customized network function data path, which is specifically tailored for the runtime settings that we have. So the idea of dynamic compilation is not something new in computer programming. Traditionally, there are a way to improve performance of software programs to use compiler techniques such as profile-guided optimization, also called PGO tools. They basically work by collecting a profile of the application while running, and then use the result of this profile to recompile the application. So the first question that we asked ourselves is, can we really use these PGO tools also for software data planes to improve the performance of software data planes? So we took two different PGO tools, OutFDO from Google and Bolt from Facebook, and we applied them to a standard DPDK firewall application available under the standard DPDK repository. And the results that we got are the one that you can see in this figure, where we managed to get around let's say 4% of performance improvement when using AutoFTO and Bolt combined. So basically this testbed was done by collecting the profile offline of the application and then compiling the application using this profile. After this performance test, now we said, okay, but is that really all that we can get now from this type of application by running these kind of tools? And we started with a set of observation. We analyzed the packet processing code, and we let's say saw that there are some features and the performance of this type of code is deeply influenced by some domain-specific metrics, domain-specific knowledge. For instance, the way we access a specific instruction table, the content of this table, or the type of traffic that the application is receiving. What is important to note is, again, that generic PGO tools do not have access to these domain-specific metrics, since they are made to work for every type of software application. Now, in addition, since the data plane performance change depending on the runtime variables or the type of traffic, let's say an application that has been compiled with a PGO tool with a specific profile collected offline does not produce an application that can, let's say, provide the same performance when these runtime settings change. So, in order to evaluate or to measure this performance dependency of this class of application from domain-specific metrics, we start with a couple of observations. So the first observation is that we can see that most data plane programs, software data plane programs, are developed as single monolithic blocks. There are different features which are implemented in the data plane, but at runtime, just a subset of these features can be enabled. The thing is that basically the dynamic configuration is unknown at compile time, so the programmer has to embed the entire logic in the program. And then at any point in time, it can be possible that many features go unused, but we still pay the cost of having these features enabled in the data plane. So to demonstrate this, we took again the DPDK firewall application and we configured this firewall just as a TCP-based intrusion detection system, where basically we placed a set of TCP pure TCP wildcard rules generated class bench, which is a tool that allows to create realistic synthetic traces. And we can see that the original data plane is the one that you shown in this figure. We receive all the traffic goes to this ACL table that contains only TCP rules. And then we said, okay, let's add some domain-specific knowledge and modify the application by having this knowledge. So we know that inside the table, there are only TCP rules. So basically what we can do is to add a branch before the lookup and skip the table lookup for instance, for UDP traffic and apply directly the default action for this type of traffic. By doing this very simple change manually in the original code and let's say testing with in a scenario where we send 90% of traffic that is TCP based, so basically it goes to the ACL lookup, and just 10% which is UDP. For the firewall application, we already got almost 5% of performance improvement. We did the same for an eBPF application, which is Katran. Katran is the Facebook load balancer that is used in their production environment. And we again took Katran and we configured Katran as an HTTP load balancer, removing all the processing by going through the code and removing all the processing that is unrelated to TCP. In this case, we got almost let's say more than 12% of improvement. So the first takeaway that we can have from this observation is it is possible to specialize networking code for slowly changing inputs. For instance, the content of the tables, the type of flow rules, the control policies, and this can improve the performance. So we can get really advantages from doing that. The second observation that we said before is that software data planes are let's say the performance of software data planes are dependent also on packet level dynamics. So the idea here is to apply some optimization that are based on the type of traffic that we are receiving. So again, we took the DPDK firewall application, we configured this application with 1K rules, and we started sending an ISQ traffic where 5% of flows and 95% of traffic. Again, we did a very simple change in the pipeline. We basically add the cache for these top flows where we give we skip the lookup in the table and we directly give the result of this lookup. And we noticed that in the green box, as you can see in this figure, we managed to get almost 42% of improvements, by adding this knowledge of the type of traffic that we have for the DPDK application. Same for the Cadran application, where we got almost 24% of improvements. So from this second observation, we have our second takeaway, basically that if we really want to maximize the performance, we should specialize the code with respect to the inbound traffic patterns, according to the type of traffic that we are receiving. So as we can see in this figure, we managed to improve the performance of these two applications by applying a set of manual modifications to the DPDK and eBPF software data planes. Starting from these results, we then said, okay, but what if we have a smart compiler that is able to do such changes automatically? Now, in this case, we could improve the performance of any generic software data plane without having to do these changes manually. And this is what Morpheus does. Basically, the Morpheus compilation pipeline is built as a set of additional compiler passes, which are built inside the LLVM framework. And all the passes work at the intermediate representation level. What Morpheus does is that it converts the original data plane code into the intermediate representation, and then it applies three different steps to generate the new optimized code. This data plane is later substituted at runtime with without any traffic disruption by using a set of trampoline and indirect calls. And then this basically triggers a loop where we this triggers a loop where we can periodically regenerate, recall the Morpheus pipeline and generate the new version of the data plane code. When Morpheus is able to find that there are new optimization opportunities. So to explain you how these three different steps works in Morpheus, I want to start with an example, which is the Cadran, the famous Facebook load balancer written in eBPF. Here you can see a very simplified version of the Cadran code, and the type of operations that it does. I will explain you with this example. So basically, Cadran has a data plane which is injected in the kernel using eBPF and attached to the XTP point. And then there is a control plane component which is running in user space. When a packet is received, the Cadran data plane first starts by parsing the layer 3 and layer 4 headers, extracting this information from the packet. And then it performs a lookup into a virtual IP map where we get, let's say, the information about the backend server where we want to send the packet. Then there is also a check in the connection tracking map that basically keep tracks of the different allocation that we made in the past, so that we can always send the same flow to the same backend server in order to avoid disruptions. And finally, when we decide which is the backend server, we encapsulate the packet into an IP packet, and the packet is sent back to the original interface. So the first step of the Morpheus compilation pipeline is the analysis. This is probably the most important step of Morpheus because in order to specialize the code, we need to have a good understanding of what we are doing in our source code, of an understanding of all the possible inputs that we might receive also at runtime. So Morpheus doesn't know anything about the original data plane, the original source code. So by looking at the different statements in the original code, the different statements in the intermediate representation code generated by LLVM, we need to retrieve those information. The first step that we do in this static code analysis inside Morpheus is to perform a signature-based call site analysis, where we basically go through all the different instructions and we recognize that there are some instructions which are more important than others. For instance, lookup or update instructions in specific map, specific match action tables. At this point, Morpheus is able to understand, for instance, the return values of these instructions and how they are used in the rest of the code, or the type of key that is used in the lookup to perform this operation. Second, we do a combination of memory dependency analysis and alias analysis to match, for instance, the lookup with the updates and define a set of read-only and read-write tables. Because this information is useful in the subsequent optimization steps. So in the first step, Morpheus analyzes a code which is basically unknown, and it gets more, all the information about the structure of the code and the type of variables that are used and how they are used in the rest of the code. The second step is the instrumentation. The goal of the instrumentation is to basically generate heat maps of the different map access patterns so that we can use these statistics to drive the subsequent optimization passes. Now, to do so, Morpheus basically injects new portions of code in the original data plane in order to, in specific point of the data plane, in order to get runtime information about the type of packets that we are receiving or the most accessed entries into a specific table. All these information are stored into a sketch data structure, and they are stored into a map, which is a lastly recently used map. Now, in this way, by modifying the original code, adding new instruction into specific points, we can get runtime an idea of the runtime behavior of our program. However, adding new instructions in the code adds also an additional cost. To reduce this cost, in Morpheus, we implemented what we called an adaptive instrumentation mechanism, where basically we used a smarter code analysis in the previous step in order to reduce the cost of the instrumentation. Now, in the paper, we mention different dimensions of adaptations for this adaptive instrumentation. Here, I will just show you an example. And the example is basically using the scope where we place the instrumentation. So let's suppose that we have this control flow graph in our application, and we have two different lookups in the maps that we want to instrument. Now, if you look carefully inside this code, you can see that basically the result of the first lookup, the second lookup is dependent on the result of the first lookup. That means that the second instrumentation can be derived from the previous one, and we we can easily remove this instrumentation from the code and reduce at minimum the cost of the instrumentation. If you see in this figure, we measured let's say the percentage of the reduction in performance that we get from the adaptive instrumentation or naive instrumentation. The naive instrumentation is basically where we instrument everything. The adaptive instrumentation where we add a smarter analysis in order to reduce this cost. Finally, the last step in the Morpheus compilation pipeline is where we really perform the code transformations, where we apply the different optimization. Now, in Morpheus, we implemented several optimization passes with the possibility to add new passes as part of the framework. All the passes are written using in C++ using LLVM, so you can easily add new passes. If you understand also how the LLVM infrastructure works and how the IR code is mapped in LLVM. But the idea here that I want to give you is that there are some passes which are traffic dependent, meaning that they use the result of the instrumentation to do the changes in the code, while other passes are traffic independent, meaning they basically apply the optimization based on the runtime configuration coming from the control plane, and they don't use instrumentation, information or runtime information about the traffic to perform the changes in the code. To give you again an example of the type of optimization that we do in Morpheus, one of these is dead code elimination. As I said before, if you remember, I was saying that software data planes, depending on the configuration, have a different portion of code that may be unused. In the Catran example, it is possible to configure Catran, for instance, with no quick services. In this case, no, we still paying the cost of having the instructions that are, let's say, that handle the quick protocol, but we are not really using those instructions. So what Morpheus does is that the static code analysis finds, for instance, there is a lookup in the virtual IP map and is able to understand the type of key used and the return value, and how this return value is used later in the code. Then Morpheus analyzes the content of this map at runtime, and you understand, for instance, that all the flags in the map have the quick value disabled. At this point, we can easily propagate the value of this flag in the rest of the code. If you see this change that I made, and we can call the LLVM standard dead code elimination pass to remove all the code which is, let's say, unrelated to quick. So the fact that Morpheus is included inside the LLVM framework allows us to call also different existing optimization passes without having to re-implement them by ourselves. We just propagate runtime information coming from instrumentation, and we call the other passes to perform the changes in the code. The second example is just-in-time compilation pass. And the reason for this optimization is that table lookup is a taxing operation for software data planes. There are several match action tables, such as longest prefix match tables, wildcard tables, which are very expensive in software. Now, the idea of this optimization pass is to specialize the table at runtime depending on their content and the dynamic access pattern. Again, just to give you an example, if we have two flows that send 90% of traffic in our application, what we can do is to just-in-time compile the result of the lookup of these flows directly in the code. Again, what Morpheus does is the code analysis discovers what are the fields used in the lookup. The instrumentation is able to get which are these two top flows that send most of the traffic, And we can easily create, I mean, not easily, but maybe easily for who didn't write the code. But no, we can basically change the original code that had an if then else for each entry by caching directly the result of the lookup in the code. Now, so this is just two examples of the different optimization passes. Of course, in the paper, there are all the explanation for all the other optimization passes. Of course, when Morpheus modifies the code at runtime, the new generated code is, let's say, bounded to the runtime configuration that we have at that time. That means that this code may not be suitable for a different configuration. So in order to keep the consistency of the data plane program untouched, what we do in Morpheus, we basically need to protect the changes, the specialized code against the changes to the invariant the optimization depend on. And these changes can be made from the control plane, for instance, when a new configuration is pushed into the data plane, or from the data plane itself, when we deal with stateful network functions that update the content of a map inside the data plane. To do so, Morpheus tries to, let's say, ensures that all the different optimization can fall back to the original code by including a set of compiler guards. Now, for people which are familiar with compilers, the idea of guards is something not new, but the guard basically allows us to jump to a new version of the code, to another, let's say, checks where we can jump to the original version of the optimized version of the code, depending on some conditions. So when we realize that the conditions that we use to optimize the code are not valid anymore, we can just update the guard and skip the optimized code and go to the original one. The solution is more complex. Unfortunately, I don't have time to explain it here, but I will be happy to answer any question if you have at the end, or you can find more information in the paper. Now it's time to show you some data. I was talking about Morpheus and how great Morpheus is. So let me show you some data. We applied Morpheus to several programs, eBPF programs, and also DTDK programs. Here I'm showing you the results only for eBPF programs. What is important to know here is that since Morpheus applies the optimization depending also on the type of traffic that you are receiving, we separated this evaluation into three different boxes. A box where we have a traffic which has a high locality, low locality, and no locality. Basically, in the no locality is when the traffic is uniformly distributed, and we cannot use any information about the type of traffic or the flows that we are receiving. You can see that in the best case, let's say in the high locality, all the traffic level optimization can kick in, so we can improve the performance. We can have from 25 to 97% of improvement. In the no locality case, we can still get some improvements, and these improvements are coming from the traffic independent optimization that I was showing you in the table before. So these optimizations are not dependent on the traffic, so we can still change the code, manipulate, remove some part of the code that are not used, or reordering the basic blocks in the code depending on the configuration settings. We also evaluated the benefits of the different optimization that we applied in Morpheus by looking at the number of reduction in CPU cycles, instructions, branches, and last level cache load misses. And you can see that in the best case, when traffic level optimization can be used, we get a lot of increase the reduction in the number of load misses. Also, while in the, let's say, in the worst case where traffic independent optimization are used, we can still, let's say, reduce the number of branches, eliminate some part of the code, and then get a reduction also on the number of branches that are executed at runtime. So I showed you all the good things about Morpheus, but of course there are also some things that may not be good. We noticed in particular that in some cases, Morpheus can actually decrease the performance of the application. For instance, for a NAT network function, we showed that in the worst case, Morpheus can decrease the performance by 6%. And the main reason for this is that basically Morpheus lacks of performance prediction and feedback model. So every time we discover that there are opportunities for code specialization, we apply all the different optimization that we can. But sometimes it is possible that some optimization can collide to each other, or some optimization are not effective as we expect. And then the cost of the instrumentation basically reduce the original performance of the application. But this is the cost that we need to pay if we really want to react to traffic, to packet level dynamics. So we have several ideas to improve this. For instance, we can monitor the usage of the perf usage of the application at runtime and provide feedback to Morpheus so that he can disable some optimization or part of them, or disable all the optimization, or we can again use the static analysis to get more an idea not only on the type of variable and the structure of the code, but also the performance of the code. On the other end, we demonstrated the importance of tracking packet level dynamics, and we showed how this can improve, let's say, open up new opportunities to perform more aggressive optimizations. To the best of our knowledge, right now, Morpheus is the first work that applies those optimization for software data planes at runtime. Morpheus code is entirely open source. There are instructions to compile, install, and reproduce all the results that we have in the paper. We also provide a Cloud Lab profile that you can use to test Morpheus with a ready-to-use testbed. So you don't have to do nothing. You just clone the profile and you run your Morpheus application. And just to mention that we got also all the badges for the at ASCLOS, meaning that the results were available, functional, and reproduced. This took me a lot of time. This is why to have the results being reproduced. Just to conclude, I want to say now that we are exploring several paths to enhance Morpheus in the future and to show the real benefits of Morpheus even in real world scenarios. One of them is to test Morpheus in cloud native environments. This is something that I'm doing right now. So what I'm doing is to take Morpheus, put Morpheus in a Kubernetes environment on top of a CNI, so a container networking interface that basically is a data plane that is used in all the different Kubernetes nodes of the cluster to provide connectivity across the different pods of the services. I'm sharing with you very early results that we got by applying Morpheus to the existing CNIs. And these are the results. These are very preliminary results, but basically you can see that on the same node, by applying Morpheus on top of an existing CNI, we can get very important speed ups, between 15 to 30% of improvements, throughput improvements. Also compared to, let's say, very well-established CNI such as Cilium and Calico. Of course, there is one cost that you need to pay if you really want to use Morpheus, which is the increased CPU utilization, because Morpheus is basically a daemon that keeps reading information from your data plane in order to react to the type of traffic that you are receiving. But you can see that in this figure, and again, these are very preliminary results, so it can be more or less, but basically the increased CPU utilization that we have with Morpheus is not that large compared to the throughput improvements that you can get. And that's all. Thank you for the attention.
Thank you very much, Sebastiano. Very good presentation. Are there any questions? George, please.
Thanks, Ignacio. Thanks, Sebastiano. Very good talk. I was just wondering, you mentioned the cases where Morpheus can go wrong, as you said, the NDP, the NAT example there. And that, if I understood correctly, was because essentially you need to keep optimizing, and that ends up heading the performance. Yeah.
Yeah. Oh, sorry. No, go ahead.
Yeah. So I was wondering if there are two other moving parts in this, if I understand correctly. One is related to the code itself, and the other one is related to what is in your data plane. And so if you gave an example where you had like a 90% of your flows being served by 2 rules or something like that, and then obviously makes sense to optimize these 2 rules. So I was wondering whether you have thought of or looked at cases that Morpheus can go wrong when it comes to a more complex program. I'm not quite sure how complex these programs can be, but in theory they can be very complex, but in practice they may always be quite simple. And the other question is the same, but when it comes to having a more widespread set of rules, where then you don't have a clear winner, but you have essentially all your flows being served almost uniformly, when then it's a little bit tricky to just optimize things.
No, these are very good questions. So basically, for the NAT example, the NAT case, the main reason that we noticed that the reason for this performance decrease, let's say it depends a lot, as you said, in the type of traffic that we were sending. Of course, if I send just one flow and I cache the only flow, I can get very important speed up. But this is not a very let's say a test that I will show in the paper. But let's say in the NAT example specifically, we were noticed that the way the code was written, but also the way that NAT works is that you perform a lookup into a connection table, but then having, let's say, the code, even if you, let's say, most of the overhead was coming from updating the flow directly in the data plane, because you perform the NAT and then you write in the connection table that you performed the NATing for this specific flow. But then if you want to really understand what are the runtime flows that are used in the NAT, you need to instrument it. But this instrumentation was taking really most of the resources, and the improvements that we were getting by caching, let's say, some of the flows or removing part of the code was not enough. This can be possible that, I mean, one reason can be it depends on how you write the code. Of course, if you write the NAT code in a way that contains a lot of garbage, a lot of instructions that we can remove online, maybe we can show some improvements. But in general, no, what I showed here in what can go wrong is that there are no safety measurements right now in Morpheus that ensures you, oh, Morpheus always provides you good performance. So it is possible that because of how you write the code, no, you cannot get speed ups. So that's the first question, right? Does it answer your first question?
I think so. Yeah.
Okay. The other question is that related to let's say testing Morpheus on more complex scenario, and this is what exactly we want to do. We want to do right now. So basically, we want to take Cilium, which is or Calico, which are very complex softwares written in eBPF. It's like contains different eBPF programs which are deployed on different nodes. So it's not just a single program; it's a set of different programs. And we want to test Morpheus now to see if Morpheus works also on real world scenarios. According to the first experiments, it looks so. So because you can consider in the Kubernetes scenario, we have a cluster with thousands of nodes, and we have the CNI which is deployed on every node. But then we have a lot of services, and every node in Kubernetes contains a mapping rule for all the different services that are deployed on all the other nodes. But generally, a given node receives traffic for a specific service or receive always the same type of flows in a given time frame. So if we can really optimize with Morpheus the pipeline according to this runtime knowledge, we can get this type of speed ups.
Okay, thank you.
Thank you.
Cool. More questions? Ron, sorry, I think you were about.
I have a question. I think this is a very cool project and talk, so thanks for giving it. I was wondering, like you mentioned that if the traffic changes, this could affect the performance of Morpheus, right? Because you optimize for one thing, then traffic changes. So I was wondering, like, how vulnerable is Morpheus to some attacker with some low bandwidth? Like, if I do like a pulse wave attack where I keep on bringing the attack volume up and down, can I make Morpheus degrade the performance of the system? Or
no, this is a very good point. I think this point, and you're completely right. I mean, this is, let's say, is more related to again what can go wrong. Of course. So basically, right now, we have this fallback mechanism where we can say, oh, if you changed the runtime performance, or you change the invariance that the optimization depend on, you just jump to the original code. So you don't execute the code that is created by Morpheus, so you just jump to the original code. But then as Morpheus right now keeps recompiling, keeps trying to create a new optimized version. And as you said, this is very vulnerable to attacks because if you know what are the optimization that Morpheus does, you can actually harm the performance. And this is, in my opinion, one of the things that we want to add in Morpheus. Let's say making the compiler smarter. Because if you notice that for a given time frame, you are recompiling too much time, and the performance that you are getting are not the one that you expect, you should stop recompiling, or maybe you should disable some optimization, because this is you don't have the advantages of using Morpheus anymore. So right now, this you're right. It is possible to do this type of attacks in Morpheus. Let's say in the future, in my opinion, extending Morpheus to make it smarter or adding a performance prediction or feedback model can help to reduce this problem.
so I think, like, something that would be interesting is like trying to guarantee that as long as the attack volume doesn't exceed some threshold, no harm can be done, or something like that. Because you don't want a tiny attacker to be able to throw off your system.
Yeah, maybe you should add, let's say, yeah, you try, let's say, to look at the different times, all the times that you keep recompiling, and maybe if you notice that the performance are still good, you just don't do anything. But if you notice that the performance will degrade for, let's say you stop and then you restart, but then you can maybe increase this time. Or you stop completely to recompile, depending on the type of attack.
Right. Thanks.
Right.
Do we have more questions? I see Kyle rising up the hand.
Hi, thanks very much for the talk, Sebastiano. The question I had is sort of a twin to Rand's question, in the sense that I suppose he's looking at more adversarial characteristics. I'm wondering, like, I suppose just now you're running the compiler continuously or at fixed intervals. So I guess, have you looked into, say, using perf maps or something in the eBPF programs you're generating to try and like track per packet latencies and processing times to maybe determine when, say, the underlying traffic distribution has changed and the optimizations you're applying no longer really work?
So you mean just use perf to get the information about the type of traffic? Sorry, not the type of traffic. How the program is behaving?
Not just using perf, but I suppose maybe like sampling timestamps for a handful of packets to understand, okay, like the median processing time for packets was 50 microseconds before, and then say your traffic distribution changes between day and night, and now it's taking on average 100 microseconds versus a baseline of 70 in an unoptimized version of the program.
Yeah, basically I have in the paper, I have some results. I was looking, no, they are not in the slides. In the paper, I have some slides where we show also the latency for the latency that you can get when Morpheus is applied. So basically, we use the same approach that you mentioned. We timestamp the packet at the source, and then we use our hardware timestamping to just make sure that we are measuring the right let's say the right latency, and then we send, let's say we send the packet through the pipeline that is optimized by Morpheus. So we send the packet back and we measure the latency. I don't have the results, but they are again in the paper. But the results are again we can get a very important reduction in the average latency by applying Morpheus, and the main reason is again coming from these this set of experiments, because since you are reducing the number of last level cache load misses or the number of branches or instructions that are executed, you are basically decreasing also the latency of the per packet program. No?
Okay, that makes sense to me. Thanks.
Thank you.
Do you have another question? Well, looks like we don't have any more questions. I think that we have asked you quite a few, Sebastiano. So maybe we'll let you go with this.
Yeah, that's fine. Thank you. Thank you very much for listening.
Thank you to you for the presentation, and hope everybody has a nice weekend.
Thanks a lot.
Great presentation, Rob.
Thank you.
Yeah.
Thank you.
Thanks.
Bye, everyone.
Bye-bye.
Bye, everybody.
Bye. Bye.